These are the upscaled and colorized lessons of Alexander Lippisch. Lippisch was a pioneering German aeronautical engineer renowned for his significant contributions to aerodynamics, particularly his work on tailless aircraft and delta wing designs. His career spanned crucial decades of aviation development, marked by a persistent exploration of unconventional flight concepts.
This is a model of the first airplane who ever flew. A model of the Wright Brothers airplane of the year 1903. This historical event took place at Kitty Hawk in the dunes of North Carolina on the Atlantic coast. It was December 17, and the Wright brothers, there were two of them, Wilbur and Orville Wright, they made at this day, at this morning, 4 successive flights with this machine. The first one, the first flight, lasted 12 seconds. This is the first takeoff at this first flight under the direction of Orville Wright. And the last flight on this day covered a distance of 852 feet and lasted 59 seconds. They were all on a horizontal course, all the flights, and the wind they flew against it was a gale of 24 miles per hour. So that if you compute this and think that they would have flown the same thing in still air, then you come out that the last flight covered about a distance of 3,000 feet and was made with a speed against air of 34 miles per hour. Now, the question is, how did they achieve this magnificent performance at a time where practically nobody else could ever match such success? Well, if you go back and see what was there on aviation and on knowledge about aeronautics before the Wright brothers. Well, we know, for instance, that in 1870, this Frenchman, Alphonse Pénaud, showed this little powered model of an airplane which contains mainly all the features. It has a wing, it has certain control surfaces, it has a little motor, it has a propeller, and is driven by the propeller through the air. And on the other hand, there were several people who began to test models, and there was one, the engineer Otto Lilienthal, who from tests with models, he concluded that it would be the best thing to fly a man-carrying glider and test the results of his measurements with certain wing-shaped surfaces, cambered surfaces. You know, a camber is a curvature of the wing, so it's hollow underneath and round above. And he tested this with gliders and showed that in this way you could get a certain amount of experience in flight, even if you did not have an engine which would propel this airplane in a horizontal course. Now, from the knowledge of Lilienthal, others tried to fly manned gliders. And among them, there was the American engineer Octave Chanute, of whom you see here the picture, who actually contributed several new ideas to the construction and design of such gliders. His main contribution is, in my opinion, the structural design of a biplane. The two superimposed surfaces connected with struts and braced out with wires. This was conceived by Chanute because he was a structural engineer. He built several bridges and designed all kinds of appliances for railroads. And in this way, he knew how to build a light and strong framework. All this was known. And when the Wright brothers began with their interest on aeronautics, which was in the years of about 1897-98, they discussed these things and they drove exactly the right conclusion of it. That means they found out that all this gliding with what we call today a hang glider, that means with a glider where the man hangs in it and controls the motions of the glider by shifting his own weight, would not be good enough to control a larger machine. And they invented at once a control system which now made it possible that the man was fixed in a certain position and moved certain levers, and with these levers he could move the surfaces. He could, for instance, warp the wings. This was the first model they ever tested as a kite. You know, they could warp the wings like this. They could shift the wings forward and backward, and all this with certain mechanical helps, and in this way could be able to control larger machines. After they had conceived this, in 1899, they began to test gliders of their system, and to be able to do this gliding with at a spot where they had good conditions, that means wind and free space. They found this spot in Kitty Hawk at the coast of North Carolina. Now, they, through these years, 1900, 1901, and 1902, they tested several successive glider types and improved it so much that in 1902, they had a glider which performed exactly as they thought it should be. It was completely controllable, very stable, had a large wingspan, much larger than anybody else had ever tested, and they flew in winds where nobody with a hang glider would ever dare to fly in it. With this system developed, they were able to go on and try to build a powered machine. Now, to build a powered machine at this time, it was necessary, first of all, to have an engine. And since nobody could build them an engine, they built it themselves. And they built an engine better than anybody else could do it. A 12 horsepower engine which had a weight of 150 pounds. And they used exactly the system of their 1902 glider, but they had to make their powered machine, as you see here, this is the same scale, larger, because the weight was larger and the machine with the operator would weigh 750 pounds. That means they tried to fly with a power loading of 62 pounds per the horsepower, which never in later years was ever tested. And they tried to fly this machine against such a storm, because, you know, 24 miles per hour on the coast with a December storm which was there is not only a strong wind, but it contains lots of gusts, and you must have a machine which is fully controllable, otherwise you wouldn't be able to fly in such weather. Now, they took off this machine, not from wheels as it is done today, but they built themselves a monorail, as you see it here in this picture. This is the rail from which they took off. And they placed the machine on a little trolley which runs along the rails. And they hooked the machine on before they took off. Then they started the engines, and after they were run in, they unhooked the machine, and it moved by the thrust of the propellers against the wind, and after about 40 feet of running on the rail itself, he lifted the machine up in the air and flew against this strong wind, which was at this time, 24 miles per hour. So that actually the machine over the ground had only a speed of 10 miles per hour. Now, these first flights, which showed that it was possible to fly a powered machine with this low horsepower and to control it in strong winds, was the beginning of the further tests of the Wright brothers. See, after they had performed this in the December of 1903, they transferred their experimental work to a place which was near their hometown in Dayton, Ohio. And there they operated improved aircraft in the years 1904 and 1905. And towards the end of the year 1905, they actually had solved the flight problem most completely, since they were able to circle their fields many times and fly times of, well, until the fuel run out or until the water supply in their radiator run out, actually about, well, 40 minutes or so. That means it proved completely that they were able to control their machine very efficiently and to fly around as they wanted to do it. So these years are the beginning of aviation, and the work which the Wright brothers did necessarily initiated several other people to try to build also flying machines. As you know, when one man has shown that it is possible, then there is much more confidence to do it yourself and more confidence on others that they would be able, if they would build a good engine, to fly with such a machine. See, the Wright brothers themselves now did not only experiment and build and design this first flying machine, but they also made very excessive tests in a small wind tunnel, which they built in their shop in Dayton. Actually, these tests are the first wind tunnel tests, practical wind tunnel tests on wing surfaces, on different shapes of wing surfaces, on different shapes of their cross sections. That means wing sections and all this. And they derived from these experiments a very keen knowledge of the design of such aircraft. On the other hand, see, when they wanted to build their powered machine, there was nobody who could ever make them, for instance, a propeller. Nobody knew anything about a propeller for an aircraft. So they not only had to build a propeller or to design it, but they had to make a propeller theory and to find out in which way a most efficient propeller had to be shaped. And they solved this problem in a very complete way and actually put two propellers at the rear of their surfaces, two very large propellers, so that they would have a very good efficiency. And by gearing them to the engine with a bicycle chain and crossing one of the chains, you see, the one of the chains is crossed, they had counter-rotation on the propellers so that they would eliminate the torque of the engine completely. All these features on the Wright machine show that they had a very extended knowledge of designing an efficient aircraft, much more than anybody else had at this time. Now, after having solved the problem, well, they went to negotiate with different governments whether they would be interested to buy their invention. Well, what they found out was this, that nobody believed that they could ever do it. So finally, it came out that they had to show it. They didn't want to show it because they thought, well, when we show it, then somebody else sees it, and then we have all the trouble that they imitate what we have done. But nevertheless, in the years 1906 and 1907, all their negotiations didn't lead to anything, so that finally, in 1908, they had to go and demonstrate the machine. And now, to demonstrate it in this country, to the government and to the Army Single Corps, and on the other hand, to show it in Europe, they had to separate. And Wilbur Wright went over to Europe, to France, and there to Le Mans, to demonstrate flights there, while Orville Wright went to Fort Myer near Washington to show the flying machine, which was on a contract with the Single Corps of the Army. We have, from this time, a few films of these early flights. Now, when you see these films, you must be aware that the speed of the films at this time was not what we have today in a modern camera, because, well, the films were not very sensitive. So what you see goes much faster, actually, than as it was done. See, their speed of taking the film was probably 12 or 16 frames per second, and you see it today with 24 frames per second. So therefore, don't bother that they fly so fast and that people move like in a Charlie Chaplin film. This is only due to these old films. But you see there, first of all, their device to take off. Now, see, they didn't want to take off from wheels because they found out they needed too much power. They didn't have that. So they built themselves a device which is a launching device to take off again from rails. And they had a derrick tower with a big weight on it, and this was then guided through a long rope on their track, which was here, and pulled now the machine which was standing on this trolley. This would be their machine. So, and then after they run the engines, they unhooked it and took off with this launching device. In some of the pictures, you see this, and you see how they pull this big weight, I think it is 1,200 pounds, up with several men. And I remember very well myself, I have seen Orville Wright flying in Berlin. When we waited for a flight, the first thing that we knew we were near to something like this was when the man came and pulled this big weight up. Now you see it in the film, and let's watch this. Now, to show you some of the most successful airplanes from the early days of aviation, besides of the airplane of the Wright brothers, we have here some very beautiful models of these airplanes. And let's look first of the most successful competitor with the Wright brothers. This is an airplane from Glenn Curtiss. He worked together with Herring and Graham Bell. This machine actually represents his airplane from the years 1909. It's called the Goldbug. It's propelled by a 4-cylinder, 35 horsepower engine, a design of Curtiss himself. It is also known as the so-called Albany Flyer, because with this machine, Curtiss flew from Albany to New York and won several prizes, among them the prizes from the Scientific American, and also competed very successful in aeroplane meets at Reims in France. You see, this machine contains mainly the same features as a Wright machine. It has in front the elevator, which he can move with the wheel there. It has, except instead of warping the wing, it has separate aileron surfaces on both sides, which is the same as the wing warping, and there's back there the rudder, and has also a pusher propeller. But he took off from wheels. Now, this was the most successful American besides the Wright brothers. In Europe, this was mainly the success, and progress in flying was mainly done by the Frenchmen. And this represents here a model of the airplane of Henry Farman, who made with this airplane the first flight in one circuit of the length of 1 kilometer in the early days of 1908. I think it was in January. This machine had no lateral control. It had only the elevator in front and the rudder at the rear. And he tried with the dihedral, you see this has a little dihedral, with the dihedral to make turns only with the rudder, which was quite difficult. It is propelled by an 8-cylinder Antoinette engine, which had 50 horsepower, and you see again the features which they had taken from the Wright brothers, the elevator in front and the biplane design. Now the tail must remember you on the tail of a kite. You know, the Hargrave kite, the box kite, was in some way also a model of the first airplanes, or at least some people derive from this type of kites their airplanes. And in this way they had such a surface back there. Now, besides of Farman, the most successful Frenchman was, as you know, Louis Blériot, who in 1909, with this little machine, which is much smaller than all the other early types of aviation, crossed the channel from Calais to Dover in, I think it was July 1909. Now, this machine is different. You see, it is a monoplane. It had also the wing warping and has a tractor propeller driven by an Anzani engine of, as I know, about 25-30 horsepower. This engine, air-cooled, was not a very reliable one, but at least he could cross the channel after a rainstorm cooled his engine in such a way that he reached the coast on the other side. He wouldn't have reached it if the rain didn't cool the engine. He had contributed to aviation one very important thing. You see, he had a stick. Instead of having these handles that all these others had, he had one stick, a wheel with a stick, and on this the wires which go to the surfaces. And by moving the stick around, he controlled this airplane. Therefore, he is in some way the inventor of the modern type of airplane control. Now, I can only tell you a little bit about these early flights and these early developments. But if you are more interested, and you should be, in the history of aviation, which is so exciting, you might find a very good source of information in these books, which I have here. At first, these are the papers of Wilbur and Orville Wright, which were now printed and edited by McFarland from the Aeronautics Division of the Library of Congress. This is an exciting story, and even if this is a big volume, I will tell you that you read it with more interest than the most exciting mystery story you ever have read. Another book which tells in a very nice manner about the first time of aviation and about the performances of the Wright Brothers and also their personal life, which I cannot mention here, is this book from Fred Kelly, The Miracle at Kitty Hawk. In our next lecture, I will tell you something more about the discovery of the dynamic lift. That means of the evolution of the cambered wing section. To give you just a little glimpse in what we will see, I have here in the tunnel one of these sections, and if we have the smoke lines on, then we can see the flow pattern, which we will discuss in our next lecture. Until this time, goodbye and auf Wiedersehen. In the previous lecture, we have talked about the invention of the airplane. And we were going through all the different stages of this development. We have seen that three major problems had to be brought to a solution. The first problem was the lift problem. That means to make with proper wings or any kind of surface enough lifting force so that we could carry the airplane aloft. The second problem was the problem of control. That means to design a certain system where we could keep the attitude of the aircraft in a proper position and go with the airplane according to the will of the pilot. The third problem was the problem of propulsion. This problem means that we have first an engine and on the other hand a propulsive system like propellers and other propulsive devices. And we have to invent and to design this. If we solve the three problems, we can build an aircraft. Now, they are certainly of equal importance, but you might admit that if we did not solve the problem of lift, the work on the two other problems wouldn't have been of much value. And therefore, since lift is a major problem of aircraft invention, we will talk at the present time about the dynamic lift. Now, we know not much about any activity in the early times of history, and we have only a few sagas or something like this, which are true or not true. The only man who really was working on this problem in a more modern way was the great genius of the Renaissance, Leonardo da Vinci. And I will give you here some quotations from his books, which actually are a big volume, and we can only take a few remarks of this great genius of the Renaissance.
The pressure exerted by the wings on the air is the same as the pressure of the air around the wing. Can't you see how the wings of the eagle striking the resistant air sustain his flights in the extremely thin air at high altitudes? You see how the wind over the ocean, repulsed by the full-blown sails, speeds up the heavily loaded vessel. From these proofs, you can conclude that man, too, will be able to master the resistance of the air. With large wings skillfully designed, he will exert the pressure on the air and master its motion so that he will be able to lift himself from the ground.
The work of the great genius Leonardo da Vinci was lost. And when the Frenchman Montgolfier invented the balloon, the lighter than air, most people thought that this was the solution of human flight. It took quite a while until people had to realize that a balloon itself is certainly a very fine instrument for investigations, but it's not the solution of the human flight as we have it today. And physicists began again to search for the true source of the dynamic lift. The first instrument which was known to men, which would fly as heavier than air, was the kite. We don't know exactly who invented it, but in the last centuries, the kite was used as an instrument for research in the atmosphere. Such kites were developed by the Australian Hargrave, and we have a little box kite here as a model in the wind tunnel, and we can see how it flies. When I turn the wind on, the kite goes up. I turn it down, the kite falls down. There it is. Again turn it up, and now if we introduce the smoke, we can actually see how the flow around the kite behaves and why we get this lift. The lift force itself is indicated by the direction of the line which holds the kite. We see that a certain pressure on the surfaces of the kite gives this lift. We will see that even better if we only mount one flat plate into the tunnel. Now we have a flat plate in our smoke tunnel, and we see that if we have no angle of attack, that means no angle between the plate and the flow line, we certainly have no lift. If we turn the plate up, we see that the flow is slowly deflected downwards and a lift results, which is mainly created by pressure from underneath. If we turn it higher, we see very well that behind the plate on the upper surface, there is a dead air zone behind the plate, which comes out even more if we turn the smoke down and observe now when I start the tunnel again, as this. When we turn it more up, then a violent oscillations begin, a phenomenon which we will mention later in another lecture. This example was used from the famous scientist Helmholtz and Kirchhoff as the first example of explaining the lift, the dynamic lift, on the flow of a flat plate. They took this example where we have here a dead air zone and the flow goes around like this. Now, it's obvious that if you disregard the friction forces, the pressure necessarily must act perpendicular to the plate and causes a lift force which is also perpendicular to the plate. If you resolve these forces in the resultant force in a lift force which is rectangular to the oncoming flow and a drag force which is in the direction, then you see that you can, from calculating the resultant force and knowing the angle, we can find the lift and the corresponding drag. From this theory, which I can explain here only very short, it was concluded that to fly a heavier than air, a considerable amount of power would be needed. When we take, for instance, an 800-pound aircraft with a man in it and a machine, and let's figure out a man would probably weigh 200 pounds, and we would have probably 200 pounds structure. Then we would need an engine of 400 pounds, which on the basis of the theory should develop 100 horsepower. Now, at this time of the theory and of this early development, which was 1870 around, no engine was known which would give so much power for just so few weight. Heavier than air will not fly. This was the conclusion of the theory. And if there wouldn't have been any independent thinkers who still searched for other means of dynamic lift, this probably could have been the death sentence of aviation. Among these were two young engineers who were lovers of birds and observed all kinds of birds, and among them the big water birds, the storks, which gave them the possibility to see more clear what the action of the bird's wings would be. Now they tamed some and measured them. And so they came out that such birds, which they had, would weigh 8 pounds. The bird. And the theory, as I explained it before to you, stated that we needed for each 8 pounds 1 horsepower to fly. So this birdie should have actually 1 horsepower. Now it's obvious that this couldn't be, because the natural horsepower weighs about 800 pounds. And if you think that a bird would have probably a more efficient muscular system and other advantages due to its smaller size. You could probably reduce this weight ratio of 1 to 100 into a weight ratio of 1 to 10, a power ratio of 1 to 10. Well, and you could conclude from such estimation that this bird would then have probably 1/10 of a horsepower for horizontal flight. That means the Lilienthal brothers concluded that natural flight was at least possible with 80 pounds per horsepower. Now, there was no theory known at this time where you could derive such a thing. The only way to prove their point was, again, the way to do experiments with wings like the wings of birds. And there Lilienthal built himself a kind of a whirling arm, which you see here in this picture. And there he measured first the straight wings, and then he began to measure cambered wings. That means wings which are hollow in its cross-section. This is straight and this is cambered. If you look at the bird doesn't have straight wings. The bird has cambered wings. That means they are hollow underneath and rounded above. And when you now observe in our smoke tunnel the flow on a cambered wing, you will see at once that this is so much more advantageous compared with the flat plate. The cambered wing guides the air over the upper surface very smoothly, and we have no dead air zone above and behind the wing. When we now turn the angle of attack to higher values, then we see that the upper surface begins to stall, as we call it, and again the dead air zone, as we know it from the flat plate, develops. But when we turn the angle of attack down to 0, that means to a position where leading and trailing edge are at the same level, we see that still the deflection of the flow is there and we have lift. This was one major point of Lilienthal's investigations, which showed that the original theory could not be right, who explained the lift as pressure from underneath. The main lift must be the suction, the low pressure developed on the upper surface. And to prove this, he used a little simple gadget, a propeller, or might be called a helicopter rotor, which is completely flat underneath and has a cambered surface above, a cross-section like this. Now this can move in this or this direction and gives lift. So if I turn it here, you will see that without angle of attack we have lift. Now watch this. He published all these tests and his observations on bird flight in a book, The Bird Flight as the Basis of Aviation. But even if a thorough investigation of his work would have shown that he discovered the real source of dynamic lift, nobody paid much attention to this publication at this time, which was 1888. He couldn't do much about it. And what did he do was to build the first man-carrying heavier than air aircraft, to build gliders, with which he could fly from a hillside downwards, gliding through the air with the power of gravitation, like a sleigh on a hillside, and measure the gliding angle, measure the speed, and in this way establish the power which was necessary to carry such an aircraft in a horizontal course through the air. He didn't want to do only this. He wanted also to imitate the soaring flight of the birds on the upcurrent of a hillside. When you have here a hill and the wind is blowing against it, then you have an upcurrent. And in this upcurrent, you could fly with your glider without losing any height. He tried this several times and improved his gliders, and finally found that he needed more and more wind. And on one of his last tests, which he wanted to do with this machine, he went out in a strong wind, and since he didn't care very much for the control of these gliders, he actually controlled them with shifting his own weight. He was caught by a strong gust, thrown up 100 feet in the air, lost control, and dove to his death. Before he lost consciousness, he uttered the words, "Sacrifices must be made." How many courageous men have since this first accident on a test flight given their lives for the conquest of the air? On their sacrifice, our knowledge is built up. And scientific achievement is not only accomplished by the men on the desk and in the research laboratories, but by the heroes of aviation who paved the way for this new conquest of the air. The final theory of the dynamic lift of an airfoil was developed by the two scientists Kutter and Zhukovsky. Kutter, a German, and Zhukovsky, the father of the Russian aeronautical science. A modern wing section is never a thin cambered plate, but it is now a streamlined cambered plate to give space for the elements of construction which are in such a wing, like the spars and other construction elements. You can easily imagine the shape of such section if you think that we first have a streamline like this, actually what we call today a symmetrical airfoil. And if we bend this, then we get a cambered airfoil like this. We have now installed one of those airfoils actually between this one and this one in our smoke tunnel, and here it is. You see, due to the rounding of the nose, the flow goes smooth over the surface, and even if we increase the angle of attack, it still holds on the upper surface. Our stalling point, which was originally much lower, is now put into higher angles of attack, which makes it possible to fly at large speeds and low speeds. Well, the main lift, as we have seen it before, was the suction on the upper surface. And this is caused by a higher speed over the upper surface, which you can see here from the narrow streamlines. But you can see it much better on a high-speed movie, which we might show you now, which is made with so-called pulsating flow. That means we enter into the tunnel pulses of the smoke, which we interrupt periodically, and this timeline, which goes now over the wing section, shows us the difference in speed on the upper and the lower surface. I think this picture speaks for itself. The death of Otto Lilienthal caused many investigators to take up the search, the development of gliders, and the further test of airfoils as proposed by Lilienthal. Among them were the two young Americans, the final inventors of the aircraft, the brothers Wilbur and Orville Wright from Dayton, Ohio. With great ingenuity, they tested gliders and they built themselves a wind tunnel and made in this first successful wind tunnel many experiments on different shapes of wings and airfoils. Unfortunately, these tests were not published until after the death of Orville Wright and are now composed in this big publication of the Smithsonian Institute, a very valuable book. At the time they tested this, the case Lilienthal against scientific theory was not yet solved, and they had to decide whether or not the tangential, the negative tangential force, as Lilienthal pointed it out, existed. What is it? See, the original theory pointed out that the force, the resultant force, is rectangular to the flat plate. So lift and drag can be calculated from this. Lilienthal showed that the drag is much smaller than predicted by the theory. That means that his resultant force he measured is ahead, in front of the perpendicular line which you draw towards the so-called chord of the section. Then when you resolve it, then you find that in this line of the chord is a force which points forward, the so-called negative tangential. Now, this is proved by the measurements, but to prove it to you here, I have a little simple experiment in this tunnel where we have a wing section on rails, and when I put the wind on, I turn the wind, then what happens? If the negative tangential exists, then this airfoil should run upwards on the rail against the wind. Now watch it. And there is a proof. If we have a little smoke, then we can even see it with the smoke lines, like this now. Well, this final proof of the tangential and the small tangential showed to the Wright brothers that it would be possible to design an aircraft which would carry a man. The famous flights of the Wright machine, December 1903, were made with a power loading of 63 pounds per horsepower. The next time we will talk about the control system of aircraft. And from the invention of the Wright Brothers, we will go through the different systems until we show how a modern airplane is controlled.
Aviation, the art of aeronautics, began with the dreamers, inventors, and daredevils who dared to defy gravity. The journey of aviation was nurtured by pioneers like the Wright brothers, whose first flight marked a historic milestone. The role of aircrafts in world wars was groundbreaking, dramatically changing warfare strategies. This initiated a technological evolution in aviation, transforming the simplistic wings of a biplane into the thunderous roar of jet engines. Let's journey through the ages of aviation. Behind every great aircraft, there were great minds. These visionaries, like Sir Frank Whittle, the innovator of the turbojet engine, redefined air travel. Then there's Skunkworks Kelly Johnson, the genius behind the SR-71 Blackbird. His designs combined speed, stealth, and power, crafting machines that dominated the heavens. The contributions of these pioneers have left an indelible mark on the canvas of aviation, shaping the course of history and inspiring generations of engineers and aviators. Each epoch in aviation history gave birth to extraordinary aircrafts, each with their own unique features and roles. The Lockheed SR-71 Blackbird was a marvel of speed and stealth. The F-105 Thunderchief, a supersonic fighter bomber, was vital in the Vietnam War. The P-51 Mustang, a long-range fighter, was critical in World War II. The P-47 Thunderbolt, a heavyweight fighter, was used extensively in the same war. The A-10 Thunderbolt II, the Warthog, is a close air support icon. The Messerschmitt Me-262 marked a leap forward in aviation technology. Each of these game changers were instrumental in their eras, and their legacies still resonate today. Beyond the game changers, there are those that have transcended their practical roles to become icons. The Concorde was not just an aircraft, it was a supersonic symbol of luxury and speed. The B-52 Stratofortress, a strategic bomber, is an icon of power and resilience. These magnificent machines and others like them have become much more than just aircrafts. They are enduring icons that encapsulate the audacious spirit, the relentless innovation, and the boundless ambition that define the world of aviation. For more amazing aerial footage, and to join us in this incredible journey, check out the Dronescapes YouTube channel.
The only reason for an airplane to exist is to go fast. At the Great Air Meet in Rheims, Glenn Curtis set a world's record of just over 43 miles an hour, and the quest for speed was on. In 1913, Maurice Prévost was flying a streamlined Dépôt-Dessin monoplane at 126 miles an hour, and Europe claimed the lead in aviation speed. Immediately after World War I, quest for speed became a catalyst for the development of fighter planes. Countries which had not invested in new engines for their wartime fighters would, for reasons of national pride, invest in new engines to race them peacetime. Then, in America in the 1930s, the situation reversed itself. Civilian aircraft, like the Travel Air Mystery Ship and the GB, Waddell Williams racers, became even faster than military aircraft. The reason was simple. Same engines were available to both civil racers and military fighters. The fighters had to carry guns, bombs, oxygen, and radios, while the racers were built only for speed. The world's absolute speed record was passed from country to country, and as the racers became faster and more powerful, they also became more expensive. America's Howard Hughes could afford to build his own racer, and with it set a land-plane speed record. But the absolute speed record of 440 miles an hour was set by a Macchi MC-72 seaplane in 1934, financed by the Italian government. Then military aircraft came back into the lead as the Heikel and Messerschmitt firms competed for the title. Messerschmitt Bf-109R set a speed record of 469 miles an hour in 1939, a record that lasted for many years. When the jet aircraft came out, speed records rapidly accelerated, the British breaking 1,000 miles an hour in 1956 in a Fairey Delta II. Speeds continued to climb, finally reaching 2,193 miles an hour in 1976 by the Lockheed SR-71, alias Blackbird. While speed was the object, there were many other benefits in creating ever faster aircraft. Improvement in fuels, streamlining, lubricants, materials, and the list goes on. Speed produced not only prestige and pleasure, but also utility. The speed record setters ultimately paved the way for commercial transports, business jets, and private planes.